Good morning. Today we're going to talk about how the model of the atom evolved over time. So the first thing we have to talk about is what is an atom. So back in the day, it was atoms came from the indivisible. So what we had was an indivisible building block, something that we could bring it back to and say that this is the smallest piece of matter. So when we talk about things, we could say, all right, everything is created from these small little pieces. This started out with Dalton back in 1803, and he basically said that every single piece of oxygen or every single piece of carbon is identical. It's basically just this little itty bitty sphere that is indivisible. You can't break it down any further. Then a little bit later on, what happened was J.J. Thomson came along and he basically stated that that cannonball that he had wasn't actually the smallest thing. That cannonball or that carbon atom was actually made up of three different little pieces. So his discovery was the discovery of a negative charge and a positive charge for the atom. So basically stated that the atom wasn't only one thing, it was created with some other things. That opened up a whole new revolution. With J.J. Thomson, he found out that when he put something like an atomic beam next to magnets, you could actually alter the position of that beam. So what he basically theorized was there were negative and positive charges inside that atom. The negative parts inside that were called electrons, and the positive cannonballish part was the positive part. What he brought it close to was a popular dessert back in his day, which was plum pudding. It's not pudding at all. It's actually just a bread that has little what they used to call sugar plums or raisins to basically moisten the bread. So it isn't actually this nasty pudding with plums in it. It's literally like a cinnamon raisin bagel or a cinnamon raisin bread. You could equate that to something like a chocolate chip cookie nowadays, where the chocolate chips or the raisins in the plum pudding model were the negative charges, the positive charge was the actual dough itself. Then what happened was Rutherford came along, and when Rutherford came along, he shot a bunch of positively charged alpha particles at a piece of gold foil. This was known as the gold foil experiment. These positively charged alpha particles primarily went all through. So 99% of the particles went straight through the gold foil. What this gave evidence to is that the atoms, the gold atoms, were actually made up of mostly empty space. When we talk about the empty space that there is, we're talking about a lot of empty space. One of the analogies is if you put a baseball on home plate, that'll represent a proton or the size of a proton. The next electron or the closest electron to that positively charged center would be somewhere where the lights are, all the way past center field, past the bleachers, past the upper decks. So if you looked at a hydrogen atom, it would only be that baseball and basically like a pinhead where the lights are. The rest of it would be all empty space. So when we say mostly empty space, we're talking about mostly empty space, like 99% of the atom is made of empty space. That allowed these particles to pass through easily. Now, since the center of the atom is dense and positively charged, what would happen would be when that positively charged alpha particle coming out of that lead box would come towards the gold foil, some of it would deflect if it came too close to the nucleus. And that's how you got some of this alpha particle scattering. The next person, after we focused on the idea that there is mostly empty space, Bohr came into the idea of having these orbitals. Now, these orbitals made sense because of the quantized theory that we talked about. So what happens is these electrons have to be in a specific orbital shell. And in order to jump from one orbital to the next, you had to give a specific amount of energy. That specific amount of energy is unique to that atom. So this is when we could use those photo specs and we could actually identify atoms, all because of this quantization of energy of when an electron goes from an excited or a ground state to an excited state, and then from an excited state to a ground state, releasing the energy as light. The electron cloud model kind of builds upon the Bohr model, or builds upon all those models, even the Rutherford model of empty space. And instead of saying that they are these fixed shells, the electron cloud model or even the quantum model, any of the modern day models, basically say that those train tracks that Bohr has those electrons on aren't really train tracks. They're more like streets where a car can go. So those would be the most um, probable locations for an electron, but an electron can be in other locations. And then last but not least, when we talk about basically back to Bohr, so something like this couldn't happen in the Bohr model. If we look at the red dots compared to the yellow dots are where they are most probably going to be, where they're on those fixed train tracks. So this would be like n equals 1, n equals 2, n equals 3. These red dots would be where the electrons can't be. And for this course and these purposes, these red dots would not exist because they are not on those fixed tracks. The last thing would be just to talk about these fundamental forces of nature. Now, there's going to be 4 fundamental forces of nature, and we're going to talk about them later on in much more detail. But just to understand a few of these things, the strong force, electromagnetic force, the weak force, and the gravitational force. Kind of talked about this a little bit in class about how the gravitational force is by far the weakest force. Now, though, it's even much, 10 to the 20 or so weaker than the weak force. Now, the weak force and the strong force are kind of the same exact types of forces. They work in a very, 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 very short range that only happens in the nucleus. When you go a little bit beyond that, which still isn't that far away, but it is far in relation to, again, when we look at that baseball analogy, when you talk about a bunch of baseballs on home plate, the next thing that it's closest to, the electron, is all the way out in where the lights are. So that's a much farther range. That would go with the electromagnetic range. So the electromagnetic range works on protons and electrons, but it also does work on the short range, which is protons and protons. The strong and the weak only work for the nuclear stuff, which would be proton to proton or proton to basically some kind of neutron force, basically preventing the protons from expanding and going further away. That's the whole lesson. Hope you enjoyed it. Be safe.